Welcome to 13Cubed. In this episode, we're going to take a look at a tool from Eric Zimmerman called MFTECmd, which can help us parse the NTFS MFT, or Master File Table, and file system journals. But first, let's take a step back and review some important concepts relating to file system journaling. Now, if some of this sounds familiar to you, we actually covered much of this in a previous 13Cubed episode called NTFS Journal Forensics, but even if you've watched that, stay with me because this episode will cover many of those concepts in more detail. Firstly, though, what is file system journaling? Well, at a high level, it's a transactional record of all the changes made to a volume. In the event of a crash or a power failure, the operating system can use the information stored in these journals to roll back or undo changes and pick up where it left off. The overall goal is to maintain the integrity of the file system and to hopefully prevent catastrophic events from occurring. In that previous episode I mentioned, we used Advanced NTFS Journal Parser, or ANJP, to look at this information. But as of this recording, that tool is no longer available. Many of you reached out to me asking if I knew of a suitable alternative, which is what prompted me to make this episode. So we're going to be looking at MFTECmd, which can help us parse some of these artifacts and fill the void. If this is your first time taking a look at this though, you may be wondering, why should I care? I mean, seriously, why is this even forensically relevant to begin with? Well, the answer is, it's because we can use the journals to find evidence of things like file creations, deletions, renames, and more. The journals may be one of the only ways to prove that a file once existed on a machine, even in some cases where anti-forensics was used. So it's a big deal. The first of the two journals we're going to talk about is called the UsnJrnl. The actual file is $UsnJrnl, and it's stored under the $extend directory. There's actually a couple of alternate data streams within $UsnJrnl, and they are $J and $max, but it's $J that contains the meat, the actual data we're after. $J is stored as a sparse file, so it can appear to be multiple gigabytes in size. Now, when you think of UsnJrnl, think high-level changes. This provides an efficient change monitoring solution. So it may come as no surprise that backup or antivirus software can use this to monitor changes or deltas to files. The information, unfortunately, may only last days to weeks on busy systems. The typical size is 32 megs. And some example operation codes or opcodes associated with UsnJrnl are things like file create, file delete, rename old name, and so on. Pretty sure that just by the name alone, you can determine what those things mean. Like, what do you think file delete means? All right, now let's talk about $LogFile. $LogFile is located in the volume root, so it's not inside of that $extend directory. Now, this one tracks detailed, low-level transactional changes for NTFS. It provides file system integrity and resilience, and it records the actual data that changed, but it may only last hours to days on the primary boot drive. The typical size is 64 megs, and some of its example operation codes include things like add index entry allocation, initialize file record segment, etc. So just by the names of the opcodes alone, you can see that it sounds more detailed, right? And there are also more opcodes associated with this journal, which makes sense because, as I said, $LogFile is more detailed and low level, whereas $UsnJrnl is high level. So the both of them together, as you saw, don't have extremely long lifespans. But fortunate for us, we can sometimes use volume shadow copies to extend that event horizon. In other words, we can pick these journals out of volume shadows that may exist on the system and pull this historical data. This could provide increased visibility over weeks or maybe even months if you're lucky. All right, so you're here for the demo. It's one thing to look at some text on a slide, but it's a whole other thing to see it in action. And this is what you guys are looking for. So we're going to be using KAPE to acquire the NTFS master file table, or the MFT, and the journals. We're then going to use MFTECmd to parse the MFT and the UsnJrnl. But wait a minute, what about the $log file? Did I mess up and leave it off the slide? No, and the reason for that is because as of this recording, MFTECmd does not yet parse $log file. It will in the future, but as I'm recording this, it does not. When you look at the help associated with MFTECmd, you'll actually see $log file listed as an option. But again, it's not here yet. We'll then analyze the results in Timeline Explorer, which if you've watched 13 Cubed episodes before, you'll know it's one of my favorite forensics tools. And that's pretty much it. So let's get started. Okay, we're in the Windows 10 virtual machine that we're going to be using for the demo, and you'll notice that I have an Explorer window opened and we're looking at the tools KAPE directory. These are the files that are part of a normal KAPE distribution. You'll see the directory's documentation, modules, targets, and a few files including the KAPE binaries themselves. But what I want to draw your attention to is the targets directory, because I want to talk to you about how we're going to grab the forensic artifacts that we're after. If we take a look at the targets, we're going to find that there are several pre-existing ones that will help us grab these artifacts. So if I open this up, within this location, you're going to see several different directories that nicely organize the types of targets that we have. And if we take a look at the Windows directory, that's the first thing I want to draw your attention to, because there are 3 KAPE targets in this location that I'll highlight here for you. That's $J, $LogFile, and $MFT. Those are the 3 files that make up the trifecta of what we're after. The same 3 files that we had used in the ANJP utility in that previous 13 Cubed episode. But as mentioned, $LogFile, as of this recording, is not yet supported by MFTECmd. Nonetheless, it wouldn't hurt to grab it anyway, because at some point, the tool will support that artifact. But check this out. Let's go back and go into the compound directory here. As it sounds, compound would be a target that is made up of other targets, a target of targets, if you will. And if you look at this one, you'll see one named filesystem.tcape. I wonder what's in there. Well, let's go ahead and open it up. At the top, you'll see the standard metadata that's part of any KAPE target or module configuration file. But check this out. Below that, the first 3 artifacts that we see are $MFT, $LogFile, and $J. Again, $J is that alternate data stream that's part of the UsnJrnl file. That's where the meat of the data lives that we're after. So we can just use file system as the KAPE target. That's the bottom line here. That's the only target we need to use to grab the artifacts that we're after. So let's go ahead and go up to our Windows terminal, and you'll notice that I have an administrative PowerShell command prompt opened. I'm going to run kape.exe. The T source is going to be C:, of course. Our target, as just mentioned, will be file system. The destination I'm just going to put on this demo user's desktop. I'm also going to go ahead and instruct KAPE to create a VHDX container. We do have to specify some kind of identifier for the container here. I'll just use demo. And by default, this will be zipped, compressed. So again, the target source or T source is C:. The single target we are using is that compound target called file system. The destination is the desktop. We're telling KAPE to create a VHDX file, and it will be zipped by default. So as you can see, we're off to the races. KAPE's doing its thing, and I'm not going to sit here and make you wait on this. I'm going to fast forward this, and then we'll pick up from there. And as you can see, this took just over 45 seconds to complete, as listed right here. All right, so we should now have the data on our desktop. So let's go ahead and minimize this Windows terminal. And as you can see, we have a couple of files here. Really, it's just the zip file that we're after. We do, of course, have the log, but that guy right there is what we need to take and move over to our analysis workstation so that we can continue our demo. So let's do exactly that. All right, I have moved the zip file from the virtual machine onto the desktop of our analysis workstation, and you'll see it right over here. Let's go ahead and unzip this so that we can expose the VHDX file within it. So I'll just use the contextual menu option for 7-zip, extracting it to its own directory. Let's go ahead and open this up, and there's that VHDX file. All I need to do is double click this, and Windows should automatically mount it and assign the next available drive letter of F : in this case. If we go into $extend, you'll see $J, which is part of the $UsnJrnl, and there's $MFT. Those are the two artifacts that we are specifically interested in, and of course you'll see the other artifacts available there as well within that VHDX. Let's pop open the Windows terminal. You will see that I have an administrative command prompt and I'm in the Tools Zimmerman directory. Let's run MFTECmd without any options and go up to the top and take a look at the most important option, which is -F. Using -F, you can specify that $MFT or $J. You will see $LogFile listed even though it's not yet supported. At the bottom, we have some examples of how to use it, but if you've used other Zimmerman tools, you'll be quite familiar with the syntax. Pretty straightforward. We'll clear the screen and go ahead and point at first the $MFT. So we'll use -F and we'll point to F:/C/$MFT. Okay, so far so good. --CSV will specify the location into which we would like the CSV file created. CSVF will specify that name of the CSV file, in this case mft.csv. And well, that's it. That's all we really have to specify. Now you'll notice that I've pressed enter, and this is in real time, so I haven't sped this up or anything, but while I'm talking, it's chewing through that MFT, and you'll see the processed message showing it took just under 9 seconds, and it found about 274,000 MFT file records. So that's it. It's written the MFT CSV file. All we have to do now is process our other artifact, which is the $J file. So same deal, -F, point to that, which is in $extend/$J. Once again, we'll use --CSV to specify the directory into which we want that CSV file written, again, being the desktop. And then for the CSVF file name, I'll just call this, I don't know, UsnJrnl.csv, which is a little more meaningful than just $J.csv or J.csv. All right, so that's pretty much it. There's UsnJrnl. It took just over 1 second to process. It pulled out, looks like 276,000 entries. And that's all there is to running MFTECmd. In the final section, what we're going to do is grab these CSV files, pop them open in Timeline Explorer, and take a look at what we have. So let's jump into the final section of the demo now. We're now in Timeline Explorer, and the first thing I'd like to direct your attention to are the 2 tabs in the top left. You'll notice that we have both CSV files opened, and we're currently looking at mft.csv. So let's start by taking a quick look at the available column headers, of which there are quite a few. So we have the MFT entry and sequence number, along with the MFT parent entry and sequence numbers. We have the parent path and file name, which are of course very important, the file size, and then we have the first of several columns containing timestamps. So let's scroll over and take a look at these. Notice that we have 2 columns for created, 2 for last modified, 2 for MFT last record changed, and 2 for accessed. So that is going to be our B, M, C, and A timestamps, if you're familiar with the MACB nomenclature. The ones with hex 10 are our $standard_information timestamps, and the ones with hex 30 are our $file_name timestamps. Remember that standard information timestamps are those that are accessible by the Windows API. That's what you're looking at with Windows Explorer, for example, whereas the file name timestamps are, in theory, only accessible by the Windows kernel. So often we can compare standard information and file name, and if we see a discrepancy there, as in this column, which does a lot of it for you, where the standard information is less than the file name, that might be indications of time stomping. Though not everything that would appear here means it's evil, because some of this is naturally occurring behavior on a Windows system. Also notice there is a column for sub-second zeros here. What that means is, because of the extremely high precision used by Windows with regards to file system timestamps, which, by the way, is hundreds of nanoseconds elapsed since January the 1st, 1601, if we happen to see a timestamp with 7 zeros, in other words, the subseconds are all zeros, well, that would be a little odd, don't you think? That can certainly indicate time stomping, because what do you think the chances are that a file would have a creation or a modification time that had exactly occurred in the all zeros subsecond precision? In other words, all 7 digits were zeros. That is probably not going to happen, and that in and of itself is behavior that may indicate time stomping occurred. So we have 2 different columns there that can help you quickly look through things that might indicate time stomping. One other important thing to note here, and you may have already been thinking this as you're watching the video, but notice that there are quite a few timestamps that are missing. They're just blank. Well, first off, the ones that are missing are in the columns with hex 30 at the end, which, as a reminder, are our $file_name timestamps. When you see this, it means that the timestamp that would have been in that location is exactly the same as the corresponding timestamp in the adjacent hex 10 column. In other words, the $file_name timestamp that would have been there is the same as the $standard_information timestamp adjacent to it, so it's left blank. This provides several benefits, including a much smaller overall file size, but the primary benefit is less noise to have to walk through when looking for entries where the 2 timestamps don't match. So it's just kind of an automatic focus into that area, because that implies those timestamps don't match if you see a value there. Otherwise, it would be blank. So I just wanted to point that out, because that may be a question that you have as you look through this data. All right, before we move away from the MFT, let me do a quick search to show you how easy it is to look for something within the MFT. So under parent path here, I'm going to specify the desktop directory for our demo user, and you can see that we have 4 hits, the last of which does not have the in use checkmark next to it, which means it's an unallocated MFT entry, one that is available for reuse. And that's actually from a previous VHDX file that was on the desktop that I since deleted. You can see the file size, and if we scroll to the right, you can see those same timestamp columns that we already covered. So very easy to search through the MFT to get a snapshot in time view of what was present on the file system. All right, so now let's go ahead and move over to the UsnJrnl. And here the column headers are pretty self-explanatory, but there's one in particular that I want to point out to you, and that is the update reasons column. That's where you're going to find those opcodes as you saw in the intro for this episode. Remember things like file create, file delete, rename old name, rename new name? Well, that's where you'll see those opcodes and where you can easily filter on them. So pretty neat to be able to know where that is and actually be able to see those specific operations in the journal. We could filter, for example, on file delete and see the files that were deleted. All right, so let's go ahead and in the top right, I'm going to type in apg.exe, which is the name of an executable I placed on this demo system. It's a password generation utility. Not that that's important. But at the very top, you'll see the file create update reason. And at the very bottom, you see one called rename old name. But notice the entry number. Let's go ahead and filter on everything with that same entry number and get rid of our search now. So now we're looking for everything on the file system with that entry number. So I'm going to highlight this for you so it'll make more sense. But if we scroll all the way to the right here and then all the way down, check out the story that can be told with what you're looking at. At the very top, we have apg.exe and we have a file create update reason. And then at the very bottom, we have a file delete for demo2.exe. So what has happened here? Well, it turned out that what I did was I placed apg.exe onto the file system. I then renamed it to demo.exe, then renamed that to demo2.exe, and then deleted it. And everything I just said there can be told through what you're seeing on screen. You can see the file creation. You can see the renaming from the old name of apg.exe to the new name of demo.exe. And then you can see the rename again from the old name of demo.exe to the new name of demo2.exe. Pretty neat, right? And all we did for that, as a reminder, was we searched for a particular file, apg.exe, we found its entry number, and then we filtered on that entry number, getting rid of that previous search. In other words, show me everything, not just APG, but everything that has that matching entry number. And there we saw all of that evidence. So I hope you see how useful these artifacts can be, both the MFT and the UsnJrnl. All right, so that wraps up this episode. And just to quickly recap what we did, we started out by using KAPE, and we used a compound KAPE target called file system to go after the artifacts in which we were interested, specifically the $MFT and the $UsnJrnl, or even more specifically, the alternate data stream $J within the $UsnJrnl. So that was pretty easy. Very easy to obtain that with KAPE. We ended up creating it in a zipped VHDX file. We then took that zip file over to our analysis machine, unzipped it, mounted it, pointed MFTECmd at it to generate the two CSVs. Then we popped open those two CSVs in Timeline Explorer and started our analysis. And that's pretty much it. I hope you found this information useful. And as always, I'd like to thank you for watching. Thank you for subscribing, and I'll catch you in the next 13 Cubed episode.